is favorable for it to go to the pure s orbital, but the bonding and non-bonding electrons, they will prevent it, and it cannot go further into that. So what we see, because of these types of repulsion between the bonding and the non-bonding electrons and other factors, what we see, the tetrahedral, which was supposed to be tetrahedral in structure, it becomes a distorted tetrahedral. So here, particularly in the case of small size elements like N and O, the steric effects also come into play. But in larger atoms, such as what happens, like that of phosphorus, arsenic, antimony, selenium, tellurium, then the steric effects may not come into play. So for larger atoms, the reduced hybridization energy of more p character in the bonding orbitals is seen. So here in figure 2.18, we can see the sp3 hybridization in the bonding orbitals. So this is here, it is 3s, it is 3p, and the resultant change in the sp3 hybridization here it has been shown. So now, how does this bond energy, which changes with hybridization, it decides, we know that this bond energy, it decides which of the geometry will be stable or not, because this is a very important factor which will decide. There are many possible geometries for different types of molecule, but out of this only certain structures are stable, and those can be decided by looking into the hybridization and the corresponding bond energies. The lobes of the sp hybrid overlap more effectively than the undirected s orbitals, the two lobed p orbitals, or the diffused orbitals. Whichever gives better overlap is preferred even at the cost of higher promotion energies. So this is one of the rules, is that whenever there is a better overlap of the different types of the orbitals, then with the structure, with the geometry, with the maximum overlap, even though the energy is high, but the geometry, when we consider that there is a maximum overlap of the orbitals, that geometry is considered to be the most stable. Now here in table 2.7, it shows the effect of the differences in hybrid bond strengths by the bond lengths in MXN molecules, where there are two types of radius are here, is that is the equatorial radius and the axial radius, and they are the different bond lengths, they have been presented here in table 2.7. So an sp3 orbital, we know, is mostly seen as a combination of pz dz square hybrids and spx py hybrids. So two linear hybrid orbitals, they bond axially and for trigonal equatorial bonds for the same sp2 type. Now we have seen from experiment that when the electronegativity of the substituents on the phosphorus atom differ, suppose like we take a mixed chlorofluoride, here it is an example of a mixed chlorofluoride like PClX and F5 minus X. This is a general representation of a mixed chlorofluoride, or the alkyl phosphorus fluorides like RxPFF5 minus X. The more electronegative substituent occupies the axial position, and the less electronegative substituent, it occupies the equatorial position. Now this is actually an example of a Bend's rule. So in general, the Bend's rule, it states that the more electronegative substituents, they prefer the orbitals that have less S character, and the more electropositive elements, they prefer the orbitals which has more S character. So although this is quite an empirical rule, the molecular orbitals calculations considering the chlorofluorides of phosphorus, they mostly follow this Bend's rule. So this is one example of Bend's rule, is the chlorofluorides of phosphorus. Then another example of the Bend rules is provided by fluoromethanes. So these fluoromethanes, we like, particularly for example, it is CH2F2. So here in CH2F2, the FCF bond angle, it is less than 109.5 degrees. So that indicates less than 25% S character. But when we have the HCH bond, it is larger, and the CH bond, it has more S character. So that is one of the case when we talk of fluoromethanes. So here similar results have also been observed for bond angles in other fluoromethanes. Now this phenomena, particularly for fluoromethanes, is called as apicophilicity. So because it is it explains which substituent it will occupy the particular orbital in the TBP structure. So, and it is also well seen in a series of oxysulforates. So these are certain, these the details have been provided in the other chapter in the second semester. Now, Bend's rule is also consistent with Vesper model or the Gillespie's Vesper model. So, the Bend's rule prediction, the important characteristic of this Bend's rule, that the highly electronegative substituents, it will attract p character and it will reduce an electronegative substituent. So, supposing doubly bonded oxygen, despite we know that oxygen is highly electronegative, they still search for the orbitals which have more s character. So that is how Bend's rule explain various types of geometries of molecules. So now coming to geometrical and optical isomers. So we know what are isomers. So here isomerism basically, particularly in metal complexes, that is those coordination complexes, isomerism has been broadly classified into two types. One is structural isomerism and the other is the stereoisomerism. So here the structural isomerism, it has been further subdivided into many types. So the structural isomerism, it consists of ionization isomerism, hydrate isomerism, ligand isomerism, linkage isomerism, coordination isomerism, coordination position isomerism, and polymerization isomerism. So these are the various types of isomerism that we come across in coordination chemistry. But since in this course we will be talking about stereoisomerism, and stereoisomerism has been particularly, it consists of two types. So these two types are geometrical isomerism and optical isomerism. So these two, geometrical isomerism and optical, we will be focusing. So we'll start with the general concept of stereoisomerism. So stereoisomers, they have this actually refers to the arrangement of atoms in 3D or in space. So geometrical isomerism, it occurs when the ligands, they assume different positions around the metal. Like for example, if we consider the compound PTNH3 whole 2 Cl2. So in general, this compound, it has a square planar structure. So two possible arrangements for this molecule, for this complex, it can be shown. So here the central metal atom is platinum. So in one arrangement, the chlorine, both the chlorine atoms and both the NH3 atoms, they can be placed in one side. And in the other arrangement, here the two NH3 and the two chlorine atoms, they are present or they can be placed in opposite to each other. So in the first case, that is when they are adjacent to each other, this isomer is called as cis isomers. And when both the two ammonia molecules or the chlorine ligands, they are opposite to each other, they are called as trans isomers. So generally, geometrical isomerism, it consists of mostly two features, that is, one is the cis isomer and the other is the trans isomer. But this type of isomerism is not possible for complexes where coordination number is 2, 3 or 4. That is, if the molecule, if the complex is linear, or if the complex has a trigonal planar geometry, or either it is tetrahedral in nature, then geometrical isomerism is not possible for such type of complexes. So the minimum that when the complex has the central metal atom in the complex has a coordination number of 4, but the geometry should not be tetrahedral, it should be square planar in nature. Now when we look into square planar complexes, there are different types of configurations that is possible for square planar complexes. Like here it can be Ma4, that is, there is one central metal atom and 4 ligands are attached to it, but all the ligands are same. Square planar complexes can also be of the type Ma3b. So here it indicates the central metal atom is M two different ligands are attached to it. That is, what the ligand is A and B, but A is three ligands are attached, three in number, and the B ligand is one in number. And square planar complexes can also be of the type MAB3. So here these are all the different types of two different A and B are the types of ligands, and it indicates their number. So however, here these are for such cases geometrical isomerism is not possible. As we can see here in the diamine dichloridoplatinum example that is shown here, we can see this complex is a square planar complex of the type Ma2B2. Even Ma2BC, four different ligands, that is MABCD and MMA2. So this type of ligand, that is AB, represents here in this case double A whole 2, it represents a bidentate ligand. So such type of square planar complexes, they show optical isomers. So like, to understand this, a few examples it has been shown here. Like when we take a compound square planar complex of the type Ma2B2, like for the example that we have discussed here, platinum, the two NH3 ligands and two Cl ligands. So the isomers possible here, they are called as the cis and the trans. Like again, we will consider a square planar complex of the type Ma2BC. So here in this complex, three different types of ligands are present, that is A, B and C. Here A indicates ammonia, B indicates bromine and C indicates chlorine, and A2 means ammonia is present in two numbers. So even for such type of complexes, the cis and trans isomers are also possible. Now we will consider a square planar complex which contains four different ligands, that is M is the central metal atom and it contains four different ligands, that is A, B, C, D. So even in this case, the three different types of arrangements are possible, and thus we can see geometrical isomers is possible in such type of complexes. Now also bridged binuclear planar complexes like PtCl2, I2, P83, it also exists in three isomeric forms. So these are bridged complexes. Why they are called bridged complexes? Because you can see the metal, two central metal atoms here, they are present and they are joined through a bridge. So here in such cases, what happens here is we see the transform, we see the cis isomer, and there we also see a symmetrical isomeric, unsymmetrical isomeric form. So six coordinated, that is the octahedral complexes, we know for octahedral complexes what happens, they also show geometrical isomerism. So when the coordination number is 6 for the central metal atom, then the arrangement, it can be of the type Ma4B2, Ma3B3, Ma3B2C. Also, it is of Ma3B, A3BCD, Ma2B2CD, Ma2BCDE, and the last case is where the M is the central metal atom and A, B, C, D, E, F are all six different ligands. So in this case, all these arrangements would give rise to geometrical isomerisms. Even we can see which contains one or bidentate ligands, they will also give geometrical isomerism. So we see particularly in comparison to square planar complexes, octahedral complexes, a large number of isomers are possible. So also because the possibility of arrangement of the ligands in an octahedral complex is much more, so that is why the number of isomers that can be geometrical isomers for octahedral complexes is much large. Also, there are other factors which also influences the formation of the geometrical isomers. Like if we increase the number of different ligands, then the possible number of isomers also increases. Like for example, we will take a complex Ma2B2 type. Here in particularly for Na2B2, here the coordination number is 4 and it is a square planar complex. So for such type of complexes, only two isomers, that is the cis isomer and trans isomer, is formed. So when we take For particularly here, if we take an octahedral complex of Ma3B3 type, so here, since it is octahedral and the coordination number is 6, we again get two isomers. That is, one is called as the facial isomer and the other one is called as the meridional isomers. So here it is important to remember that cis isomerism and trans isomerism, they are shown by square planar complexes. But when we have an octahedral complex, we also get two isomers, but they are called as facial isomers, that is mostly written as FAC, and the other is the meridional, that we can write it as MER. So in facial isomers, the three ligands of one type, they form the one triangular face of the octahedron, and the remaining other three, they come on the other side of the octahedron. Here it has been shown. So here, if we look into this figure 2.23a, so this is an example of a facial isomer. So once we look into the figure here in the octahedron, the A, the three A ligands, they are present in one side of the octahedron, and the three B ligands, they are present in the other side of the octahedron, and that is why they are called as facial isomers. Now also there is an possibility of present of the other isomer, that is called as the meridional isomers. So here we will look into this figure 2.23b, which shows the meridional arrangement. So what happens here is, set of the ligands, they are arranged around an edge of the octahedron, whereas the other set, it occupies the opposite edge. So here one set, they occupy the edge of the octahedron. Here you can see BB, they are same, and they occupy one edge of the octahedron, whereas the other set, that is AA, they are also present in the opposite edge. So this is how we differentiate between a facial isomer and a meridional isomers. So this is when for octahedral complexes. Now here, when we write geometrical isomers, we will always be sure that the ligands must be different in each configuration. Now we will rotate our ligands in such a way so that they are present in different configurations. So it is very important that we write, or the position of the ligand is given appropriately. So for example, here for we have fixed the cis position for the two ligands A and wrote all possible configurations. Here it is shown in figure 2.24. So we will take a complex Na2B2CD. This is since the coordination number is 4, this is an octahedral complex. So A2B2CD. So what here in this case, as you can see, the one set of ligand is fixed. So here AA has been fixed in all the cases, and the BB has been fixed. So when we fix these two, we get two possibilities. That is the one here, the figure 1 and figure 2. So in these cases, and also here in figure 3. So three possibilities are done. So here what happens is, once we write, we will, the arrangement of the ligands has to be proper, because that will ultimately, we cannot randomly just put any ligands. Then the writing the possible ligands is actually a great practice, and it should be written very carefully. So this is all about geometrical isomerism. Now we will come about optical isomerism. So what is this optical isomerism? So optical isomerism are the isomers are those isomolecules which rotate the plane polarized light in different directions. So in these isomers, they have almost all similar physical and chemical properties. The only difference in the optical isomers is that it lie in the rotation of the plane polarized light. So such optically active compounds, they exist in pairs, and they are actually called as stereoisomers or enantiomers. These isomers, they are non-superimposable mirror images of each other. So like we have the right hand, it is the mirror image of our left hand. So these optical isomers, they are non-superimposable mirror images with each other. So any molecule, how will we know that this molecule is optically active or not? So there is one possibility, and that is called as to find out the chiral center, or what we call it as the center of symmetry. So any molecule which contains a center of symmetry or plane of symmetry, it will not show optical isomerism. So optical isomerism is observed very rarely in square planar complexes. Why? Because it contains a plane of symmetry and a center of symmetry. So the tetrahedral complexes of the type MAB2, where AB is a bidentate ligand, it can give us this optical isomerism. Here we can see, so here in the left hand side, this is AB is a bidentate ligand. The metal M, it is placed in the center, and you can see this ligand, AB ligand, and here the AB ligand, they are unsymmetrical in nature. So that is why, since they are unsymmetrical in nature, that is why they are non-superimposable mirror images, and so they are it forms an optical isomerism. So however, optical isomerism is very common for octahedral complexes of these types. Like for some example, it has an example has been shown for CO ethylene diamine 3 plus. When we look into this, is a tridentate ligand. This En here, it is a tridentate ligand. So when we look into this, here it is one ligand, here there is the one, and here three different. And when we take the mirror images, it forms non-superimposable mirror image. So this is how an optical isomerism it works. So this is the general concept of geometrical isomerism and optical isomerism. So with this, we finish the part of the second block about the main group, the structures of molecules. So these are some of the questions that you can go through. The answers have also been provided here, and you can go for your do for your own practice. So now we will start with the third unit, which deals with phosphorus nitrogen and sulfur nitrogen compounds. So here we will talk about the bonding between, first we will talk about the bonding between the phosphorus nitrogen followed by the sulfur nitrogen. So first we will begin with the phosphorus nitrogen compound. Now phosphorus nitrogen compound, they can either exist as P-N single bond or P double bond N, that is when it has a double bond. So such compounds, these phosphorus nitrogen compounds, they are either oligomeric or polymeric in nature. So what does this oligomeric means? So oligomeric means that it is comes in the form of many monomers. They join together to form a oligomer. Now when we have oligomers, it means there are 2 to 9 monomers present in it. Like if it has 2 monomers, then we call it as a dimer. If it has 3 monomers, then it is a trimer. Then the oligomeric term is generally used when we have 2 to 9 monomers, and the term polymer, it is used polymeric or when the number of monomers it exceeds 9. So polymers mostly include a large number of monomers, and such type of phosphorus nitrogen compounds, they are mostly polymeric in nature. So first we will look into how these phosphorus nitrogen compounds they were discovered. So first it was well known that phosphorus pentachloride, that is PCl5, it reacts readily with basic reagents like water or ammonia. So here you can see PCl5 plus H2O, it forms POCl3 plus HCl. Similarly PCl5 plus H2O, it forms H3PO4 plus HCl. So after this, after the reaction with water, then similar reaction with ammonia was done, and it was found that that these products were expected. But what happened was that the reactants and products, they were found to be sensitive to moisture, and it did not happen. So what happened is, then the less conjugate acid, that is the less reactive conjugate of ammonia, that is ammonium chloride, was used, and then the reaction with PCl5 it happened. Like PCl5 did not directly react with ammonia, but PCl5 reacted with ammonium chloride at 146 degrees centigrade, forming PnCl2. So these are called as phosphonitriles. So these products, that PnCl2, those are obtained, they are either cyclic or linear polymers, and they have this general formula, that is PnCl2, which is analogous to benzene, and that is why they are called as phosphagenes. So the general formula for phosphagenes is PnCl2, and here N, it indicates that this is the monomer and N is the repeating unit to form the polymer. So here the major product and the easiest to separate is the trimer. So trimer means N is equal to 3. So smaller amounts of the tetramer and other oligomers up to 8 have been characterized, but higher polymers have also existed. Now, while preparing the analogous bromo compounds, we have to add bromine sufficiently so that the phosphorus pentabromide, it does not decomposes. Now, this PBr3, we know it is highly susceptible to degradation to PBr3 plus Br2. So what happens is, to prepare this, the bromo analogous, we have PBr5, it is reacted with NH4Br in excess of bromine. So indirect fluorination of the chloride results here in this NPF2 whole 3 like compounds. Planar 6-membered compounds, they are a result of formation of halide trimers. The bond angles, they are mostly sp2, the bond is sp2 hybridization, the nitrogen is sp2 hybridized, but the phosphorus that is present here, it is sp3 hybridized. So here in figure 3.1, the two sp2 orbitals of hydrogen, it has been shown, and you can see that they contain one electron each. Here in this case, it is one electron that are used for single bonding, and the third orbital here, it contains a lone pair of electrons. So this results in the one unhybridized pz orbital. So the phosphorus, we know it uses 4 electrons in the 4 sp3 hybrid orbitals for the sigma bonding. So the fifth electron that remains, it is in the d orbital. So here in figure 3.2, we can some of the trimeric phosphagene structures, that is P3 and 3Cl6, it has been shown here, and their resonating structures, it has been shown. So here what happens, when we look into these structures, we see that it is a similarity to benzene. So once we see this, there is a similarity to benzene, so we expect that it should be aromatic in nature. However, the actual structure is not very simple, and there is the aromaticity does not arise here. The phosphorus ring, it is actually planar in nature, like the one that is shown in figure 3.2b. So and the bond distances are equal and short. All these alone, with the stability of these compounds, it suggests delocalization. Even all the phosphagenes, they are not planar, but still they are stable in nature. The pi bonding in cyclophosphagenes, it involves both the D and P. So since both D and P orbitals are present here, they give rise to D pi P pi bonding. So this is a major difference from the bonding in benzene. So in benzene, we do not come across this D pi P pi bonding, but in phosphagenes, we come across this D pi P pi bonding. The extent of delocalization and the nature of the aromaticity, they are still debatable. So here the from 3.2b, here we can see this is the actual structure of P3N3Cl6. So and this is also a huge topic of research to actually understand the structure of phosphagene. Now from figure 3.3, we see that there is a Girard symmetry of the d orbitals, and this gives rise to the mismatch of the different some signs of the wave functions in the particularly in the trimer. So Craig and Paddock, they suggested a model in figure that is shown in 3.4. Here the d extended orbital of the phosphorus atom, it overlaps with the pz orbitals of the adjacent nitrogen atoms, as shown here in 3.4a. So now here, if we look into this 3.4b, here if the d orbital, it is perpendicular to the d extended, then it overlaps here with the p orbital of nitrogen. Here it orbitals with the p orbital of nitrogen, that results in the node. The sp2 non-bonding orbital of the phosphorus, it can have an in plane pi bonding that has been shown. So here it is a very complicated structure theory that was offered by Craig and Paddock. Now there is also a alternative way to consider the structure of the phosphazines, and this was discussed by Dewar and co-workers. So what they have done is they considered that the d, x, z and y orbitals, they hybridize to give two orbitals which are directed towards the adjacent nitrogen atom here, that is shown in 3.5. So what here is, so the three center bonds, they are formed about each nitrogen. So then the delocalization over the three atom, around the around the nodes they happen, and this is how the three center two bonding, the three center electrons, it proposes the model for P3N3Cl3. Now both these models, they have been supported by evidence, yet there is the trimeric phosphazines, they are mostly stabilized by this or explained by the three center bond model. Then tetrameric phosphazines, they have more flexible structure. They are not difficult like the trimeric. Tetrameric, they have quite easy structure. Here that is NPF24. It is planar in nature, and the conformations can be seen as the tub, boat, chair, crown, saddle, and the various intermediate structures. Out of the two isolated forms of the tetrameric fluorophosphazines, the one with the chair arrangement, it is the most stable. So here we can say this structure that is with the chair arrangement, it is most stable. The other here in the figure A, this is the tub arrangement. Even though the corresponding organic compound that we call it as the C8H8 is non-aromatic, but the tetrameric phosphazines, they have aromaticity, and they are extensively delocalization also takes place. So other ring sizes have also been synthesized. Here we talked about the trimeric and tetrameric, but other ring sizes like for n is equal to 3 to 13 have also been studied for such phosphazines. Then coming to phosphazine polymers. So the polymers of phosphazine, they can be prepared, and they are also advantageous and better than carbon based polyesters. So the preparation of the polymers of trimeric chlorophosphazine, here it is shown in equation 3.8. So here upon heating, when the reaction is carried out carefully, then cross linking of the polymer of N is equal to 15,000, it can be done, and the result product that is formed, it is soluble in organic solvents. But what happens here is the chlorine that is present here, they also undergo nucleophilic attack and displacement, like as here it has been shown in figure equation 3.9 and 10. Different elastomers, plastics, films and fibers may be procured if we change the nature of the side chain. These materials, they tend to be flexible at low temperatures and water, and they are fire resistant in nature. The phosphazines are also useful as medical, as slow releasing drugs. They have also been used to form ceramics. So this is some of the common examples of polymeric phosphazines. So here, if one PCl2 group is substituted here, it forms a ring, and it forms the first, here it forms the example of the first polycarbophosphazine. Then coming to linear phosphazines. The properties of linear polyphosphazines, it differs if the R groups in the chain, they are changed, that is P double bond N, and we have R and R. So the properties also changes. So by eliminating PCl5 from NPCl2 whole 3 synthetic phosphazines are synthesized. When all the PCl cannot be removed, then an insoluble product is formed which is of no use to us. When NPCl23 is heated above 230 degrees centigrade, it forms the polymer where N is almost equal to 15,000, and thus the product forms. And here we can see that how we can, using the changing the reaction conditions, we can get a variety of mixed polymers. Here different schemes of the reactions, it has been shown. So the inorganic backbone and the organic or the organometallic side groups, they determine the properties of these polymers. Then fluoroalkoxy or aryloxy side groups in polyphosphazines, they have been used to form elastomers. So elastomers, They found great use. They have also been used to prepare iron conducting materials. Synthetic chemistry have also used this dichlorophosphazine in the preparation of various types of polymers and other compounds. Then direct synthesis of organophosphazine polymers can be done in this method, direct heating at 200 degrees centigrade. Also, there are various methods by which ring opening polymerization has been used to produce substituted phosphazine to form the corresponding polymer. So here, during the preparation of polyphosphazine, an important product is phospham, which is produced by the reaction of a highly cross-linked polyphosphazine. Here NH3 plus 2 red phosphorus at 500 degrees centigrade is forms the P2NH. PNH2 here in equation 3.16 it has been shown, and this here is the phospham, which finds it is an important class of phosphazine. Then other PN compounds, they are typically PN types. The PN bonds, they are single, but partial double bond it can arises due to the N-p-pi and P-d-pi donor bonding, as it has been shown here. The aminophosphanes, they are monomeric in nature, whereas groups are bulky when the RR dash aminophosphanes are either monomers or dimers. So here in figure 3.13, a dimer of aminophosphane here it has been shown. Then compounds with larger rings, in that is here in figure 3.14 it has been shown where larger rings they have been formed. Some of the examples of polycyclic of PN types it has been shown here. Then the next is the sulfur nitrogen compounds. So here the ring and chain compounds, the S2N2, S4N4, SNX type compounds, that is the sulfur nitrogen compounds, they have been formed. So they are actually ring compounds. The aminolysis of sulfur monochloride, that is S2Cl2, either in solution or in inert solvent. Here as you can see it forms S4N4 and plus the S8. So the product here, it is a bright orange solid that is insoluble in water, but it is soluble in some organic solvents. Although the crystals are reasonably stable to attack by air, they are explosively sensitive to shock or friction. Here in the cage structure that is shown here in figure 3.16, so the two pairs of non-bonding sulfur atoms, they are at a distance of about 258 picometers, so which is much less than the van der Waals radii. So normally when we talk of sulfur-sulfur bond length, it is 206 pm. So there must be some interactions which increases this value up to 258 picometers. So there must be some extensive delocalization. Cyclophosphazines, they have resemblance to this, but this is more complicated. We have also seen that S2N2 and SN6, they can be both prepared from S4N4. Other neutral binary sulfides, they may be obtained from it as well. When S4N4 is heated under the pressure in a solution of CS2 containing sulfur, then S4N2 is formed. Here we can see in figure 3.17b molecular structure of, this is the molecular structure of S4N2. Then also a larger number of binary sulfur nitrogen compounds and anions are known. So if we reduce S4N4 then with metallic potassium, then it yields the S3N3 minus. So this seems to be benzene analog, but if we count the electrons, then the Huckel rule is obeyed, so it is aromatic in nature. So this is how a series of sulfur nitrogen compounds they can be formed. So tetrasulfur, when it is reduced with tin 2 chloride, it produces tetrasulfur tetraimide, that is S4NH4, which is isoelectronic with S8. Now S4N4, it can be oxidized. Then if it is treated with chlorine and then trithiazyl trichloride, here it forms N3S3Cl3. So the fluoride can also be formed from this equation by using AgF2, and N3S3Cl3, it can be oxidized to form the sulfonylyl chloride. So these are some of the possibilities of the formation of sulfur nitrogen compounds. So here this with this, the sulfur nitrogen compounds and phosphorus nitrogen compounds, we finished this part. So here there are some of the terminal questions about this chapter, and the answers it has been provided. You can go through it, and with this we finish this part. We'll just take a break of 5 minutes and then resume with the second block. So now we'll start with block 2. So here in this block 2, this is mostly about organometallic chemistry. So the organometallic chemistry will first have an introduction to different types of organometallic compounds, followed by the metal carbonyls, then metal pi complexes, the clusters, different types of clusters. So in this unit, we will first begin with the introduction to organometallic compounds. So now in general, how do we define an organometallic compound? So here an organometallic compound, it is defined that those compounds which must contain at least one metal to carbon bond. So that is minimum a one metal to carbon bond must be present there. So here these metals also, it may be like non-metals like boron, silicon, phosphorus or arsenic. So it is not always necessary that it should be like typical metal, but the presence of boron, silicon, phosphorus or arsenic can also give rise to different types of organometallic compounds. So the ligands are the compounds which are get attached to the central metal atom. So they ligands, they may be organic compounds like carbonyl but not cyanide, but it should be CN, acetate, and also different types of compounds like we see as neutral molecules like H2O, NH3, they serve as ligands. So compounds like TiOE24, calcium NMe2, they are not organometallic compounds, but when we have Fe, that is the C2H5 2, these are organometallic compounds. So carbides, cyanides and carbonates, they are excluded. They do not belong to this category. Metal carbonyls, they are a special class of organometallic compounds and they have been included in a separate chapter. So now we discuss the mainstream of organometallic compounds which are dominated by the nature of this MC bond. So depending on this nature of this MC bond, so organometallic compounds, they have been classified into various types. So first there is those organometallics where the MC bond is a conventional sigma bond. So this sort of sigma bonded organometallic compounds, they particularly belong to the main group chemistry. Then secondly, the organometallic compounds, they may also form by the sigma donor, that is and pi acceptor like carbon monoxide. Then thirdly, the organometallic compounds can also be formed by the pi electron donors like for example olefins. And lastly, the organometallic compounds can also be formed of highly electropositive metals and they have been classified in a separate group. So now we know that the most transition metal organic compounds, they have immense variety in their structures and their bonding types. Now this is because we know that transition metals, they can have vacant d orbitals, and that is why they can utilize the s, p and d orbitals in their bonding to form the different organometallic compounds. So each orbital type, they can either donate or accept electron density. So just as in the bonding in coordination compounds, the d orbitals on the metal, it should match the orbitals and to form the with the s and p orbitals. So there is a very flexibility in bonding and electron transfer in the organometallic compound. So here in figure 4.1, a portion of the periodic table is given and the different types of bonding that are possible with the most electropositive metal, that is the alkali metals, the d blocks, they have been shown. So here we can see that particularly for these classes, that is for the group 1 metals, they mostly form ionic organometallic compounds. And here from beryllium to, if we look into this group to here to the boron group, they mostly form the covalent deficient structures. The d elements, they form complexes with both ionic, that is the sigma donor ligands, and also the pi donor ligands. But the main group elements, that is the particularly the p group elements, here they form volatile covalent compounds with sigma donor group. So these are different types of bonding that has been discussed here in particularly that occur in different organometallic compounds. So first we will start with ionic organometallic compounds. So they are actually a special class of organometallic compounds. Here, the lanthanides, actinides, and metals of the groups 1 and 2, which have electronegativity less than 1, they are highly electropositive in nature. So they are organometallic compounds. They mostly it is ionic in nature. But if we consider lithium, beryllium, or magnesium, they have covalent character. Their stability and reactivity is determined by the nature of the carbanion. So the compounds containing CnH2n plus 1 minus an ion, they are not stable, and that is why they are difficult to isolate. If the electron density of the carbanion is delocalized, then stable salt like compounds are obtained. Suppose we have C5H5 minus Na plus, so and C5H5 whole 2 Ca calcium, then the negative charge here it is delocalized over the pi electron. So examples of some simple organometallic compounds are like methyl lithium, that is CH3Li for group 1. We have dimethyl beryllium here for group 2 and trimethyl boron for group 13. These are some of the common examples of ionic in organometallic compounds. So then we will talk about the covalent sigma bonded organometallic compounds. The sigma bonded organometallic compounds, they are formed by most of the non-metals and also by metals which have very low electropositive character. So here the covalent bonding is formed when there is by most non-metals are taken, or even if we take a metal, but it should have a very low electropositive character. The transition metals, they form fewer sigma bonded compounds, and those are highly reactive in nature. The MC bond in such type of compounds, they are regarded as 2C2E, that is two center, two electron bonds, and the partial substitution of halogen or similar groups may take place, like for example Me3SnCl or MESnCl3. In these compounds, the MC bond it has appreciable ionic character, but the covalent nature here it predominates. So here in such type of compounds, we see that although the ionic character is present, but the dominance of covalent character can be marked. So, like for example, tetraethyl lead organotene compound here has also such type of behavior. Here the organic group it is bound to the metal by a normal covalent bond, and that is the 2C2E bond. So unlike the main group elements, the transition elements they form fewer simple alkyls or aryls. So the stable alkyl and aryl compound with are also known when other pi acceptor ligands are present, like suppose COPR3, or with other groups like CH2PH, CH2SiMe3. These are known. Then stable cobalt carbon bond is present in nature, and that is found in vitamin B12. Often, then due to coordinately unsaturated metal centers, the MC sigma bonds are weak, and such compounds decompose easily, resulting in high reactivity. Then non-classical multi-center bonding and pi complexes. So the nature of bonding in or such type of organometallic complexes, they cannot be just understood by 2C2E bond. The alkyls of lithium, beryllium, and aluminium, they depict multi-center bonding types. So for examples, such non-classically bonded compounds, they are mostly found in the transition metal compounds of alkenes, alkynes, and other ring system. Like one of the common examples are ferrocene and Zeiss salts. They are non-classical organometallic compounds. So here the such type of non-classical bonded compounds, they have been divided into two types. So the first is the organometallic compounds that have bridging alkyls, some that is dimeric trialkyl aluminium, that is Al2R3, and polymeric dimethyl beryllium or dimethyl magnesium. So here the structure of dimethyl beryllium it has been shown, and it is polymeric in nature. So here is the BE bridging, and the methyl group is attached to it. So the structure of dimeric trialkyl aluminium, since this is a dimer and it is trialkyl aluminium, so this is the trimethyl group that is attached to it, and the bridging it has been shown here. So this the Here this is the aluminum that is joined through bridges, and there are the bridging methyl groups and the terminal methyl groups. So these compounds, they are characterized by the presence of the bridges. So the metal is equidistant from each of the two metal atoms. So the nature of bonding here, on the basis of 2C2E bond, it cannot be on the as a bridging carbon, it cannot be simultaneously bonded to two metal atoms. So in case of dimeric compounds, two types of aluminum and carbon bonds are noted. So what are they? The terminal aluminum carbon bonds and the 2C2 electron bonds, while the bridging bonds, they are three centered two electrons. So here in such type of cases, different types of bonding are observed. Then comes the second class, that is the pi electronic bond, pi bonded organometallics. These are transition metal complexes with unsaturated organic compounds, where there is a interaction between pi orbital of the organic ligands and the d and p orbitals of the metal atom. The compounds with alkenes, alkynes, and cyclic compounds, they having which contain delocalized pi orbital, they are classified into this category. So some ligands are alkene, butadiene, allyl, cyclopentadiene, benzene. Some of these are examples, and the organometallic compounds of this class, they are Zeiss salt, ferrocene, etc. So here, some common ligands in organometallic chemistry, they have been shown here in table 4.1. So CO is the formula, and it is not carbon dioxide, but it is carbonyl. CH3 is methyl. This is N-butyl. CH3 whole 3C is tertiary butyl. When we have C5H5 minus, it is written abbreviated as CP, and it is the short form for cyclopentadienyl. C6H5 is phenyl, and it is written as PH3. C6H6 is benzene, and it is written as such, whereas C6H5 whole 3P is triphenyl phosphine, and it is written as PPH3. And here in this formula you can see Cn is the cyanide, and mu here it represents the bridging, mu CO and mu F. So then comes to, in this organometallic compounds, there is an important concept, and that concept is called as hapticity. So now what is this hapticity? So here hapticity means the organometallic compounds and their bonding potential with the ligands. And here hapticity is represented as eta to the power x, where x can be 1, 2 or 3. Suppose we have eta to the power 5, so it indicates penta. That is, it has a capability of binding to 5 atoms. So here hapticity can be technically defined as the number of carbon atoms within a bonding distance of metal atom, or the number of carbon atoms through which an organic ligand is attached to the central metal atom. So here we see it is eta 5 Cp. That means the cyclopentadienyl, it is here attached to 5. Here this is pentaheptocyclopentadienyl. Here it is written. So for better understanding, we'll look into this table 4.2, the classification of organometallic ligands and their hapticities. So if that is, for one is eta 1 monohapto. So monohapto means here it is the hapticity is 1. So like for example, we have ethyl lithium C2H5Li. So here the hapticity is 1. Dihapto. So here for the hapticity is 2, like for example in CF2 so it is bonded to two ligands, that is hapticity is 2. Then trihapto, here hapticity is 3. Suppose for a cyclopentadienyl ligand, it is hapticity is 5, so hence it is called as eta 5, or we call it as a pentahapto. So similarly we can organize the different types of hapticity. And here some of, in this third column, we can see some of the common examples have been provided. Organometallic compounds of alkali and alkaline metals. The synthesis, structure, bonding properties, and some of their uses. So we will start with a very common organometallic compound, that is methyl lithium, CH3Li. That is, here it exist in both solid and solution state in oligomeric form. The here oligomer we know which contains more 2 to 9 monomer species. So the tetrameric and hexameric forms of methyl lithium, it has been analyzed by the FTIR and X30. The tetrameric form here, it has been shown, the it is simplified here, it has been shown in figure 4.6. You can see this is the structure of methyl lithium and this is the tetrameric form, it has been shown here. So the tetrameric form, it means that the four lithiums here, they occupy the alternate diagonal corners of the tetrahedron, and the carbons of the methyl group, they occupy the vacant corners of the cube. So the structure of the tetramer here, of this tetramer of the methyl lithium, is very unusual. So each methyl carbon atom is above the face of the tetrahedron and it forms a triple bridge with the three lithium atoms that are on the face of the tetrahedron. So the coordination number for such case is, for the carbon atom, is 7. Even in a similar way, the coordination number of lithium is also 7. So this is how a tetramethyl lithium it looks like. Then coming to beryllium sandwich compounds. So here beryllium we will study the best method. It is to, first is that the it is done by heating the metal and adding any mercury dialkyl. Here it is shown in equation 4.1, that is HgMe2. Just direct adding of beryllium at 110 degrees centigrade, it forms BeMe2 plus mercury. So after this, the alkyl, it is generally collected with the help of sublimation and then it is collected. So what happens is, in air they are highly inflammable in nature. So that is why they are very much reactive in nature. So in the vapor phase, this dimethyl beryllium is monomeric, and the solid state structure here it is shown in figure 4.7, and it mostly resembles to that of BeCl2, where 3C 2E bonding it is found in the polymers of dimethyl beryllium. However, when we prepare an aryl of this dimethyl beryllium, we can see that in diethyl ethers it can form of the by the forming the reaction that is shown in equation 4.2. It can be shown here, that is diethyl ether, it forms the diphenyl beryllium. Cyclopy and pentadienyls of beryllium, it can be prepared simply by the reaction of NaCl plus BeCl2, forming BeCp2. Cp here it stands for the cyclopentadienyl, and here it is just direct by heating it forms this BeCp2, and the structure here it is shown herein for the BeCp2 has been shown here in figure 4.8. Now these rings, they are very weakly held together, and that is why the proton NMR shows that all protons are present in an equivalent environment. So here CpBe2 it possesses a sandwich structure, and this has also been confirmed from NMR spectroscopy. So now coming to organometallic compounds of transition metal alkyls and aryls. So we talked about beryllium. Now we will talk about different of the transition metal alkyls and aryls. So here the first is the transition metal alkyls and aryls. We will be talking about the main group elements, that is particularly the lithium, magnesium, zinc, mercury, arsenic and aluminium. They form the first metal alkyls. So they were first formed and still some of them are also been used today. So then the alkyl lithium, we know it is the reagent, the starting point of many complex organic synthesis. Even diethyl zinc, it has been considered as the first true molecular compound which has a metal carbon bond, for which Franklin is considered as the founder of the organometallic chemistry. Then we have a very important organometallic compound that we call it as the alkyl magnesium halide, that is RMgX, or which we call it as the Grignard's reagent. So it is also an organometallic compound. Then also there are various organolithium compounds and particularly organoaluminium compounds. They were found by Ziegler, which we today call it as the Ziegler-Natta catalyst. Then organometallic alkyls and aryls, they have been classified on different bases. So on the basis of the types of ligands that are present, they are classified as homoleptic or heteroleptic metal hydrocarbyls. So homoleptic are the metal hydrocarbyls where all the organic groups on the metal atom are the same. Like for example, if we take TiMe4 and VPH6, these are homoleptic, whereas heteroleptic are those metal hydrocarbyls in which the groups attached to the central metal atom are of different types. Like for example, TiMe4 minus X and Ly. So here two different groups are attached to the central metal atom, and that is why they are heteroleptic in nature. So again, organo transition compounds, they have been classified on the basis of their nature of ligands. They are classified into alkyl organometallics, or they have been classified into aryl organometallics. So organometallics with alkyl radicals, they are called as metal alkyls like TiMe4, WMe6. They are simple organometallics with alkyl radicals. Then organometallics with aryl radicals, they have been designated as SCPH3, LaPH4. So these compounds, they may be symmetrical like ZrMe4, or they may be unsymmetrical like TiMe3Bu, or they may be mixed in nature where they contain here, like in this example, WMe2CH2PH whole 4. So they are mixed, that is, they both contain alkyl and aryl ligands. So on the basis of metal atoms, the organo transition complexes, they have been classified as mononuclear or polynuclear organometallics. So in polynuclear organometallics, the metal atoms, they are linked together through bridging alkyl or aryl groups, or directly with the single or multiple bonds, or they have been in addition to metal metal bridging alkyl or aryl groups are also present, plus a additional metal metal bridging is formed. So metal alkyls as stabilized carbanions. So here we know that electrophilic alkyl groups, they were available from the alkyl halides, and nucleophilic alkyl groups, they were first found by Grignard, that is in form of RMgX. The metal alkyls that result from combining an alkyl anion with a metal cation. So as a result, what happens is the alkyl anion, it gets stabilized, and the extent of such stability, it depends on the electronegativity of the involved metal. So polar organometallics, they result from the alkyls of the electropositive elements of 1 and 2, and sometimes of the elements like aluminium or zinc. So alkyls of the early transition metals like such as titanium or zirconium, they can also very sensitive to air and water. So this situation changes as we move across and down the periodic table. That is where they are less electropositive and the compounds become much less reactive. Again, the situation changes when we reach mercury. So where the stability of the mercury carbon bond, it makes MEHG plus cation much stable in aqueous sulfuric acid and in air. So here in figure, we can the effect of here in figure 4.9, the effect of changing metal here it is shown. So here the nucleophilic reactivity of the main group and transition metal alkyls versus the electronegativity of the metal, it has been shown here in figure 4.9. So in figure 4.9, the effect of changing metal is shown, and it is seen that the reactivity falls steadily as we move from ionic NaCH3 to the polar covalent lithium and magnesium species. We also must not forget that the stability of the R fragment is also important. When as an we consider as an sp3 ion, we see that ch3 minus, it is the most reactive. When the orbital has more s character, that is for sp2 c6h5, and it is even more for when we have r triple bond C, then the lone pair is stabilized. So similar trend, it makes the acidity of the hydrocarbons increase. So after this, it was found that the Me3PTI, who made a first successful isolation of D block metal alkyl. There were after many, there has been failures, but it has mostly been found that the metal carbon bonds in transition metal alkyls, they are strong. So thus the transition metal alkyls, they do not easily, they cannot be synthesized. They decompose easily so that they could not be synthesized. And thus the reaction kinetics, they are also responsible for synthetic failures. Now several ways have been found so that the decomposition pathways can be blocked. Like first is the beta elimination. So beta elimination means it converts a metal alkyl into a hydrido metal, into a hydridometal alkene complex, which is a major decomposition path. So this mechanism, it occurs when there is a hydrogen substituent in the beta carbon of the alkene. The beta hydrogen here, the beta hydrogen comes close to the metal as the MCCH bond. The MCCH unit, it takes up a planar coplanar conformation. There is a vacant site on the metal. The reaction is faster for D2 and higher for D0. So beta hydrogen of the alkene, it is transferred to the metal and gives the product hydride. So here in this equation 4.4, the beta hydride elimination, it has been shown for CH2 case. And here you can see how this beta leads to the elimination of CH2. Now there are also various problems associated with beta elimination, but this is one of the ways for decomposition of the hydrides. Then stable alkenes. The blocking the beta elimination pathway, it prevents decomposition and form kinetically stable alkyls. The compounds in which this happen, they are shown in table 4.3. Here it is below. So here, if the alkyls do not have beta hydrogen, then the examples, these are kinetically stable. If the alkenes for which the beta hydrogen is unable to approach the metal, then it is kinetically stable. The alkyls in which the MCCH unit cannot become syn coplanar, it is also kinetically stable. And then the an 18 electron species, it will also, it does not dissociate properly, so that means it is also kinetically stable. And some of the D0 alkyls, they are also kinetically stable in nature. Now here is a special case that we'll look into. It is the structure of WMe6. So Ml6 species, mostly we know they are octahedral in nature because the coordination number is 6. But WMe6, it has a trigonal prismatic structure. So why does this difference arise? So it was previously predicted here that the D0 of the MX6 species, it takes trigonal prismatic shape. So why it happens as the methyl ligand is very small in size, and so the polyalkyls, they are formed with it, and many compounds are formed as a result of this. So the stable alkyls are also formed by this substitution, and electron withdrawing groups or bulky groups are also there. So even though the vinyl and phenyl groups both have beta hydrogens, they do not eliminate beta hydrogens readily. So that is, beta elimination does not occur. So the beta hydrogens, they are much away from the metal in these sp2 hybridized systems, and thus which does not favor for the delivery of beta hydrogen. So this may be the reason that these groups, they do not undergo the beta elimination. Plus the phenyl and the vinyl groups, that are, they have stronger MC bonds than the ethyl group. So that is why this is a typical case of WMe6. Then agostic alkyls. So beta elimination may not occur in species even in which all the criteria seem to be favorable, and this is very rare. So like here in figure 4.12, when we look into this, this is the here where is figure 1.4.12. Here in figure 4.12, particularly here it has been shown here for where for D0 alkyls. So what happens here is, so even though we have the alkyls start to be in the transition state for beta elimination, and the beta CH bond is bound to the metal in that way, somehow they are kinetically stable and the reaction does not proceed. So here from the X-ray structure and the high field shift of agostic H in the proton NMR has helped us to understand the agostic alkyls. The compound here that is shown in figure 4.12, it has D0 titanium, which does not have the electrons for the necessary necessary for the back donation. So here in the beta elimination reaction, this back donation, it breaks the CH bond, and in the absence of it, the beta elimination does not occur in the compound. Then halide elimination. So beta elimination of halide can also occur for the lanthanoids and the actinoids, along with some early transition metals such as titanium. The MF bond strength of these elements, it encourages beta elimination of the halide, and so stable fluoroalkyls, they are not formed. So then comes reductive elimination. Metal alkyls, they undergo reductive decomposition, or what we call it as reductive elimination, or both. So both the electron count and the formal oxidation state, it decreases by 2 units, and that is why it is called as reductive. Now when X here in equation 4.7, it is a halogen, then reductive elimination is not observed. Why? Because the position of the equilibrium is towards the left, and so the reactant in equation 4.7 is stable thermodynamically. But when we take X is equal to H, then kinetically facile and the thermodynamically favorable, so the reaction takes place. In such situation, it is not possible to isolate alkyl hydrates. So this reaction is generally much slower. Then stability from bulky substituents. Organometallic complexes of different classes may be stabilized by bulky ligands. For 16 electron metal species, alkyls can be decomposed associatively when it reacts with the solvent or with another molecule in the complex. So here in figure 4.14, orthotolyl complex, here it has been shown. So whether that approach is, when we look into this, that approach is blocked, it becomes more stable and it converts to this diphenyl complex. So even though here beta elimination is ruled out, alpha elimination can takes place from such type of cases. Then preparation of transition metal alkyls and aryls. So they can be prepared in 4 different major processes. One is metathesis, the other is the metallate alkylation reaction, the third is the metallate acrylation acylation, and the fourth is the oxidative addition. So in the metathesis reaction, mostly organolithium, organomagnesium, organoaluminium, organotin, and organozinc reagents, they react with metal halides. So here this happens, what happens is or other organometallic, when a reagent R, that is a nucleophilic attack on the metal takes place. Here we have WCl6, it is made to react with LiMe. So here it forms WMe6 plus LiCl. Then this is how the metathesis reaction works. Then comes the metallate alkylation reaction. This category, it represents the reaction of carbonylate anions with alkyl halides, as here it is shown below. This attack takes place from an electrophilic attack on the metal. So here if we look into this, MnCO5, it reacts with MEI, forming MeMnCO5 plus I minus. So this is a metallate alkylation reaction. Then coming to metallate acylation reaction. This involves the reaction of carbonylate anions with acyl halide. So carbonylate anions here it is shown here, and then acyl halide is CH3COL, and how here the reaction it proceeds. Then the last method of preparation is the oxidative addition. So with alkyl halides, when a 16 electron transition metal complex undergoes alkyl oxidative addition. So this happens whenever we have a metal fragment, it is inserted into the XY bond after breaking the XY bond here, as it is shown here. So this is an XY bond. The MLN complex, organometallic, here transition complex, here it is shown, and then it inserts itself to the XY bond. So this is called as your oxidative addition. So often carbene like LNM fragments, they are found as there is some similarity of inserting those fragments to XY bonds. So at this step, oxidative addition, it involves an increase by 2 units to the oxidation state. So the coordination number and the number of electrons also increases by this oxidative addition. So what happens is the metal fragment, it should be able to undergo oxidative addition only if had a stable oxidation number n plus 2. Also it has been, it should be able to accept two electrons, because we know that at oxidative addition it increases the oxidation state by 2. So here it, like, so most, it has been seen that the metal fragment must have 16 electron or less, because this is one of the most easiest approaches. So what it has, if it has a 16 electron, then again by this process it will add up 2 electrons, so that it becomes 18 electrons. But if we start with higher number of electrons, then it is a difficult process to continue. So but sometimes it has been seen that when we take a 18 electron complex, it can first lose at least 2 electron, and then it will undergo such type of reaction. So here there are various process by which we can we can calculate the number of electrons and design the synthesis of our particular compounds. Then there is the insertion method. So this insertion method can be of two types. One is the alkene insertion and other one is the carbene insertion. The alkene insertion is also called as hydrometallation. So here it means that there is a insertion of metal hydride and the alkene, like here as it has been shown in equation 4.23. So we have the alkene is C2H4 and this is the metal hydride. So here the C2H4, here it goes, and then we find that this type of, this is the final product. Then the carbene insertion, it means that the metal hydrides, they will react with carbene. Here as you can see, it is CH2N2 and then they form the metal aryls. So the nucleophilic attack on the metal, it can take place to form an alkene when often we take a Grignard or a organolithium reagent. There are many situations when electrophilic attack also takes place on a much nucleophilic metal in organic chemistry. The reaction of methyl lithium with Me2CO, both these pathways, they used to make bonds to carbon or nitrogen. So in this method of acyl complexes, preparing is has been found to this very useful, the method of insertion. So with the route of insertion, an alkene and a metal hydride, they can together, they can form an alkyne. So we must be knowing that one of the most important applications of organometallic chemistry is in the catalytic reactions. So catalytic reactions, we know that there are different types of catalysts, they have been synthesized by this type of route. So here in equation 4.26, C2H4 insertion, here it has been shown, and how different types of catalysts they can be prepared has also been shown here. Then bridging alkyls and related ligands. I mean, it has been found that alkyls, they may behave as bridging ligands. Like mostly we came across 2E3C or 3E3C, that between the metals and carbons. So here in figure 14.6a, we see these are the bridging ligands for main group elements, particularly for aluminium. So here in this case, Me4Al2, Me2, there are sharp resonances for methyl groups in the NMR. So we may say that here the bridging ligands, Me4 mu, here it indicates for the bridging ligands. Even the planar methyl coordinated with the D0, it may result into numerous bridges. And so here various types of bridging ligands, it has been shown in figure 4.16. Then coming to alkylidines and carbides. So alkylidines are two normal covalencies, that is one to each metal. They are formed by the carbon metal of alkylidine, that is Cr2. Suppose in complexes like Cp2Ta, here the alkylidine forms a double bond to the metal and it acts as the terminal ligand. So here in figure 4.17, this is a alkylidine. Even alkylidines may act as a terminal group. Here in figure 4.17b and c, alkylidyne, it has been shown. So a carbon can also bridge with four metals. Like here it has been shown in figure 4.18. We see that the carbon here has bridged to four metals. So here it is mostly we call them as clusters rather than complexes. So here we can see figure 4.19. We can also see that here the carbon, the there the carbon is also 6 coordinate. Then metallocycles, cyclic dialkyls, they are called as MCH-2N, they are called as metallocyclics. Although the metallocyclopropanes, they behave metal alkene complexes, the higher homologues, they behave similar to the dialkyls. They show interesting rearrangement, and here it has been shown in equation 4.29 to 4.30. So here the empty pi star orbitals that are present in the aryl, vinyl and acyl ligands, they have the capacity to accept electron density from the metal, thereby forming strong MC bonds. Pentahalophenyl ligands, they are very much stable and they form strong bonds. The vinyls and acyls also have eta 2 bonding models here that we have shown here in figure 4.21. Then there are the less familiar low valent sigma bonded organometallics. So here there are also certain complexes which have very low valent sigma bonded organometallics. Like for example, the here what happens in some of organoselenium, selenium and tellurium halides, here they have been shown. So here in this case they have a very lower set of valencies which differ by units of 2, whereas when we look into for transition metals the difference they vary for 1. So this can also, this lower differences can also be attributed to the inert pair effect which prevents the s electrons to take part in chemical bonding. So some representative structures of organoselenium and tellurium halides, they have been shown. So then coming to bivalent organometallics of SiGe, tin and lead. So bivalent analogues of the heavier main group 4 elements have been seen. So bulky ligands such as CH2SiMe3, CHSiMe3 whole 2, or they have been used. So but although in such cases, since these ligands are bulky, then steric factors are also, they prevent the polymerization. However, some complexes have been isolated. So what are the complexes that have been isolated? So first is the, like the preparation is by, first is by pyrolysis. So for pyrolysis we know that controlled heating either in absence or in presence of air. So but it should be controlled heating. So pyrolysis of silylins by pyrolysis of silane. So if we take a silane and heat it to temperature above 250 degrees centigrade, then we get silylins. Here it has been shown. Then also by ring contraction reaction of cyclic polysilanes can also takes place. So there are the reverse, the equation 4.34, here it has been shown. It also may have a side product of silyl radicals. So the reverse of the above reaction is a radical coupling reaction, whereas the reaction of SiR2 or SiR4, they may be considered as an insertion reaction. Then is reductive elimination. Dehalogenation reactions also provide another route of generating SiMe2. So here the SiMe2 can also be prepared by dehalogenation reactions. So in the absence of such trapping agents, SiMe2 can also be obtained from polymeric solids. So metathesis reactions, the simple alkyl or aryl stannylines, they originally represented as SnR2 and they can be prepared by the reactions of the following types, that is shown in equation 4.42 and equation 4.43. So this is the metathesis reactions that are used for synthesizing SnR2 compounds. Then metathesis reactions can also be used for synthesizing dialkyl germanium derivatives for GeCl2 here and its derivatives here as shown in equation 4.47 and 4.48. The synthetic procedures for synthesis of tin metallocycles, here they are shown here in equation 4.49 for dialkyl derivatives, here it has been shown. So these are some of the procedures by which we can prepare the organo transition compounds. Then coming to their structure and bonding. The mostly the tin and lead derivatives, they are soluble in hexane, benzene or diethyl ether, but the analogues of germanium, they are less soluble. Even though the germanium and tin derivatives, they are air sensitive, they can be still handled in air, but the lead derivative, it cannot be handled in air. So here, as we can see, for SnCl4, here at different temperatures, by varying the temperature, we can see different routes for the preparation of tin metallocycles. They can be prepared by taking SnCl, stannous chloride, as the precursor. So the ground state valence electron configuration of germanium, tin and lead can be given as Ns2 and Np2. So and these elements, they form bivalent complexes by bonding with the help of two unpaired electrons, that is the two unpaired electrons present in the Np2. So here the spx and the spy hybrid orbitals, they form two covalent bonds here. That is why they are called as bivalent organometallics. So when we move to the fourth main group elements, the bivalent derivatives, they both have an MTP orbital and also an orbital containing lone pair of electrons. So both Lewis acid and Lewis base behavior is expected from them. So here the scheme 4.2, it summarizes the chemistry of bivalent group 4 metal alkyls taking SCH SiMe3 whole 2 as a typical example. Here the scheme 4.2, it has been shown the different types of reactions with different types of reagent, it has been summarized. So stable tetravalent derivatives, they are not obtained when PbCH when the lead derivative is used. So the reaction of lead with methyl iodide, it results in the disappearance of the purple color. So it suggests that the reaction forms an transient adduct. So this is, we can see some of the general reactions of the SnCH-SiMe3 whole 2. Although this is a monomer, the crystal shows that it has a center of symmetry. The shape of the compound, it is distorted, as you can see from this structure, it is distorted, where the alkyl groups on the tin atoms, they are directed away from each other. Here, as it has been shown, as a result, what happens, this is a bent double bond that is observed in here, RMe3Si2CH here. Then complexes such as CO5Cr, SnCH, SiMe3 whole 2, it is where the tin takes up the trigonal environment. Here we can see in figure 4, the tin is present in a TBP structure. Then coming to fluxional organometallic compounds. So what is this fluxional organometallic compounds? So for this, to understand this, we will take an example. That is eta1 C5H2 whole 2, eta5 C5H2 whole 2, and the metal is titanium. So the crystal structure of this molecule, it shows two monohepto and two pentahepto CP rings, that is the cyclopentadienyl rings. So here what happens, the proton NMR, it shows a single line. So this implies that the interconversion is a dynamic process. So then it was studied that at lower temperature, when this interconversion happened between the mono and pentahepto ligands, it is very slow. But although that at low temperature, the dynamic process of the monohepto, it is prominent. So also from looking at the NMR and the data, we found that there is an exchange occurs between the eta5 and eta1 ring at 30 degrees centigrade. So we see that there is an exchange. So this is the fluxional processes that involves uh, the exchange between the the cyclopentadienyl rings in a complex. So fluxional processes that involve acyclic unsaturated hydrocarbon ligands such as allyls and allenes, they are also common in nature. So example is the pi complex that is formed between dimethyl allene and tetracarbon. Here it has been shown an example of the migration of the iron that has been shown here. So the proton NMR here below 60 degree, it shows one value, and above 60 degree, minus 60 degree, it has been one value. So we can see that there is a migration. Here it is FeCO4. Then this has migrated to this place. So such type of migration, it leads to the formation of fluxional organometallic compounds. Now coming to organocopper compounds and its applications. So organocopper compounds, they were first discovered by Gilman. So, who for synthetic organic chemistry? Now, copper can exist in Cu0, Cu1, 2, 3, and 4. But the Cu0 and the Cu species are very rare. So, various compounds with CuC, that is in plus one state, it has been formed. The Cu state 2 plus has been is the most found one in inorganic chemistry, but in coordination chemistry, it is Cu1. So the stability of the organocopper compounds are like lithium compounds. They are more stable than organocuprates. They are thermally unstable in nature. Alkyl copper compounds, they decompose very slowly, and the stability has been found to be of the order alkyl less than aryl and less than alkylyl. The thermal stability of organocopper compounds, it can be increased by substitution of hydrogen atoms by fluorine in the organic moiety, or by addition of, or by other ligands such as phosphine or amines, or by use of heteroatomic substituents. So these complexes are generally found to possess linear, trigonal, or T-shaped geometries. So lithium dimethyl cuprate, it is prepared by the equation shown in 4.52, and some of the characteristic of the reagent are: compared to carbonyl group, can take part in numerous novel reactions as it has a strong nucleophilicity. It does not react with any other ester or the chloride group that is present in the acid. It prefers to attach to the beta carbon in an alpha beta unsaturated carbonyl system, and any halogen atom may be replaced by the methyl group present in this uh, present in the reagent. Then halogen substitution. By interaction with organic halides, it forms CC bond and they prefer ether or similar solvent. So here we can see in the equations the halogen substitution. Then alkene complexes. Copper is the only metal that is involved in biological system which reacts with ethylene, and it is bond and it forms a metalloenzyme like chelating alkenes like norbornadiene or cyclic polyenes from crystals. So copper is the one metalloenzyme that is present in biological systems. So copper chloride in concentrated HCl, it can form CuCl, CH2, CH2, that is an acetylene compound. So copper 1 acetylide, it provides a useful route for the synthesis of a variety of other organoacetylenic compounds. Copper also forms carbonyls. So like CuClCO, it exists only under high pressure. So at CO pressure of 1 atm, the reaction has been shown to this. But simple carbonyl complexes, they are not stable in nature. So a series of hydrides have been obtained for copper by reacting with lithium, and they form lithium methyl cuprates as they have been shown here in equation 4.59. So here we talked in this chapter, we talked about the different types of bonding in organometallic complexes, the different types of organotin and organosilver complexes that we have talked about. So these are some of the important questions. You can go through this that has been shown here along with the, so along with the answers, the self assessment answers that has been present here with some important long questions. So here with this we finish the chapter on organometallics, and tomorrow we'll start with unit 5, that is metallocarbonyls. So with this unit we finish the class for today. Tomorrow we will again start with a new chapter on metallocarbonyls. So thank you for today.